GameSide.com. GameSide.com.
Hello, 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 hello. Time for some binary multiplication. Computers are quite simple. All they do is move some ones and zeros from RAM to CPU, manipulate change ones and zeros in the CPU, move ones and zeros from the CPU back to RAM. Repeat this a billion times a second. That last step is a doozy, so let's look at step number 2, manipulating ones and zeros. The ALU, Arithmetic and Logic Unit, is the part of the CPU responsible for binary multiplication. This is certainly manipulating and changing ones and zeros. Binary multiplication of unsigned integers is a remarkably similar task to decimal multiplication. Let's start with some decimal multiplication and look at where it's similar before doing the binary multiplication. Notice how I've set up the zeros. They're pre-filled. The 2 in 321 is really a 20, and we know anything multiplied by 20 must end in a 0. When we multiply that 2, we know it has to end in a 0. The 3 in 321 is really a 300, and we know anything multiplied by 300 must end in 2 zeros. So those 2 zeros are pre-filled for multiplying by 300. Understanding why those zeros are there is extremely important to binary multiplication. This should be third grade review. 1 times 123 is simply 123. I'm going to multiply the digit in the ones place by the operand 123 and get a result of 123. 1 times anything is always anything. That's important for binary math. Also, the 1 in 321 is in the ones place. So there's no 0 at the end of this. We are multiplying the digit in the ones place. 10 to the 0 power is 1. That's why this is called the ones place. Third grade review. 2, the middle digit, times 123 is simply 246. So I'll multiply 2 by 123 and I'll get an answer of 246. Also remember the 2 in 321 is in the tens place, so it must have a 0 at the end. 10 to the first is 10. That's why 2 is said to be in the tens place. Anything multiplied by 10 or 20 or 30 must end in a 0. The reason I'm harping on the zeros will be apparent when we get to binary math. Let's multiply the 3 by 123. 3 times 123 is simply 369. Also, the 3 in 321 is in the hundreds place, so we must have 2 zeros at the end of it. 10 squared is 100. Anything multiplied by 100 or 200 or 300 must end in 0, 0. It's important to understand why these zeros are there. 3 is in the hundreds place. It has to end in 2 zeros. The reason I'm harping on the zeros will be apparent when it comes to binary math. Sum the three values and arrive at the result 39483. Just summing up the columns here. There's an 8, there's a 5, 14, carry the 1. Binary multiplication of unsigned integers may even be easier than decimal multiplication, except for the number of digits needed. Hint, straight columns will go a long way to avoiding simple mistakes. Also notice the carry of 1 that occurs right there. Line up your math with straight columns and it's easy to total up the columns. Put in crooked columns and it's going to be very difficult, and it'll be very difficult when you get to binary math. Binary 14 times binary 13. For reference, the decimal calculation is on the left. We can use that to check the binary. 14 times 13 in decimal. 3 times 14 is 42. 1 times 14 is 14. But notice the trailing 0. This is not multiplying by 1. It's multiplying by 10. And anything multiplied by 10 has to end in a 0. Sum those up and you get 182. Use that to check the result of our binary multiplication. Before we start, let's keep in mind 0 times any number is 0. 1 times any number is that number. Holds for binary multiplication as well as decimal multiplication. Point out once again, I'm going to pre-fill the zeros. I know they have to be there. I'm going to put them in at the start. Why are the zeros pre-filled? 13, the bottom operand, is really broken down like this. 1 times 2 to the third power plus 1 times 2 squared plus 0 times 2 to the first plus 1 times 2 to the 0. Calculating that out, it's 1 times 8 is 8. 1 times 4 is 4. 0 times 2 is 0. And 1 times 1 is 1. Add that all up and you get 13. When you multiply by binary 2, which is 1, 0, the result must end in 0. So I pre-fill this 0. When you multiply by binary 4, 1, 0, 0, the result must end in 0, 0. So I pre-fill those two zeros. When you multiply by binary 8, 1, 0, 0, 0, the result must end in 3 zeros. So I pre-fill the 3 zeros. Those terms in the multiplication must end in zeros. Let's put them in now. They have to be there. 1 times 14 is 14 in decimal. 1 times 1110 is 1110 in binary. It's easy. All I'm doing here is 1 times the top operand, and of course I get the top operand. I don't know if it can get any easier than that. 0 times 14 is 0 in decimal. So 0 times 1110 is 0 in binary. I guess it did get easier. This digit 0 in the twos place is multiplied by that number right there, just like we did in decimal. And of course the result, 0 times anything, is all zeros. It is that simple. Where the second operand bit is 0, you write down a 0. Where the second operand bit is a 1, we're going to write down the top operand, or the first operand. See what I mean? Binary multiplication may actually be easier than decimal multiplication. There's clearly a 1 in the fours place. 1 times 1110 is 1110. Here's the 1 in the fours place. I multiply it by the top operand, and I get a result for that right here. Do you see why we pre-fill the black zeros? 2 to the second power is 4. Binary 4 is 100. Multiplied by 100, it has to end in two zeros. Also, 14, 1110 ends in a 0. The red 0 right here is from the top operand, the first operand. The black 00s are because it's multiplied in the fours place. 100 times 1110 is 1110 with those two zeros because it's the fourth place. Finally, there's a 1 in the eighth place. 1 times 1110 is 1110. 2 to the third power is 8. This is a 1 in the eighths place. Binary 8 is 1000. If you multiply by 1000, it has to end in three zeros. Also, the 14 in decimal is binary 1110. It ends with a 0. The red 0 right there is from the top or first operand. The three black zeros are from the eighths place. We are multiplying 1 in the eighths place, so it has to end in three zeros. 8 times 14 in binary is 1000 times 1110. And of course the result is 3 1s and 4 zeros. This is from the operand. These three are from the eighths place. That's why we pre-fill the zeros. And then we either insert zeros when the bit is a 0, or we input the first operand when the bit is 1. Add up the terms to find the result. This may be the hardest part of binary multiplication. When doing it on paper, be very careful to line up the columns nicely. The small black ones are the carry bits. There's all zeros in this column, so we'll put in a 0. There's a single 1 in this column, so we'll put a 1. There's a single 1 in this column, so we'll put a 1. There are 2 1s in this column, so that's 0, carry the 1. There are 3 1s in this column, so that's 1, carry the 1. Once again, we have 3 1s in this column, so it's 1, carry the 1. 1 plus 1 is 0, carry the 1. And there's our final result. Line up the columns and it's a lot easier. It's also important to check your result. If I write down my powers of 2 backwards, 128, 64, 32, and so on, then write down my binary number underneath my powers of 2, anywhere there's a 1, it's part of the result. This is 128 plus 32, there's a 1 under the 32, plus 16, there's a 1 under the 16, plus 4, plus 2. Wherever there is a 1 in the binary number, write down the appropriate power of 2. 128 plus 32 is 160. 16 plus 4 plus 2 is 22. 160 plus 22 is 182. It matches my decimal result. I did the binary unsigned multiplication correctly. Simple circuits. It's all about building ALUs with simple, small, fast circuits. If you look closely here, this is just the first operand left shifted 0 times. Take this number, shift it left 0 times, and that's that number. There's a 0 in this column because there's a 0 in this bit right there. Anytime you multiply 0 by anything, you get a 0 result. This is the first operand shifted left 2 times. Since we're multiplying by this column in the 4th place, we take the first operand, shift it left twice, and that's this row of our result. This row is the first operand shifted left 3 times. Since there's a 1 in this column, we'll write down this number, shift it left 3 times. Those are those 3 zeros right there. And that is the value in this row. I then accumulate the sum total. The unsigned binary multiplication algorithm is a simple loop with an addition and shift operations. Shift, 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 shift. Sum them all up with addition and you get a result. Here's some pseudocode for unsigned multiplication. I'm going to start the accumulator register with a 0 in it. I'm going to start the B register with operand 1. I'm going to start the C register with operand 2. And a simple loop of while the C register is not equal to 0, well, the C register contains this, so it's certainly not 0. I'm going to execute this code. I'm going to shift right the C register. I'm going to shift this set of 1s and 0s to the right and peel off this 1 right here. If I shifted a 1 into the carry bit, which I did, there's a 1 right there that got shifted into the carry bit. If that's a true statement, I'm going to add to the accumulator the B register and store the result into the accumulator. So I'm adding this value right here to the accumulator, and the accumulator will contain this row right there. Then here's something curious. I'm going to shift left the B register. The B register is this value. I'm going to shift it to the left and make it larger. I'll hit the end of the while loop and come back up here. While the C register is not equal to 0, that's this value right here. There's still a 110 in it. It is not equal to 0. I'm going to go into the loop. I'm going to shift right the C register. When I shift right the C register, I'm going to be shifting this 0 out of the C register. If the carry bit equals 1 is a false statement, since there's a 0 in this place, there's nothing to add. I'll skip the add. Basically, by skipping the add, I just added in 0. Once again, I'll shift left the B register. I will make this value larger. I'm going to shift it over a second time. That's where those two zeros right there come from. I'll hit the end of the loop, come back up. The C register currently has a 1 1 in it. So I'll shift right the C register. When I shift right the C register, that one right there will go into the carry bit. In the carry bit, it's a true statement. So I'm going to come in here and say the accumulator equals the accumulator plus the B register. The accumulator has this value. The B register has that value. I'm going to add these two together and store the result into the accumulator. I will then shift left the B register. I'm going to shift left this value right there for a third time. That's going to create these three trailing zeros right there. I'll hit the end of the loop and loop back up. The C register still has that single one left into it. We'll shift that to the right. When I shift that single one to the right, it'll get into the carry bit. This will be a true statement. And I'll take the accumulator, which contains the result of adding these two numbers together, and add to it the B register, which contains this value. And I will add that and store it into the accumulator. Essentially, at this point, I have my result in the accumulator. Not quite done yet. I will shift left the B register. This is the B register right there. I'll shift it left, hit the end of this loop, come up here, and the while C register is not equal to 0. Well, I've already shifted all of these bits out of the C register. The C register is 0, so we'll exit this code completely. And at this point, the accumulator contains this value right there. Do you see what I did there? What I did is I spun in a loop and I added this value, and then I skipped this one because there was a 0 right there. Then I added this to the accumulator, and I added to this accumulator. That's why it's called the accumulator. It accumulated these bits right here. That's all you have to do unsigned binary multiplication. Shift the operand and add it into the total when there's a corresponding bit into the second operand. This is unsigned binary multiplication. These ones right here have nothing to do with the signed bit. When you do signed 2's complement, this would be minus 2 times minus 3 equals 6. I'm not going to do the entire signed algorithm, but I will discuss an important part of doing signed multiplication, and that is called signed extension. In 4-bit 2's complement, minus 2 is 1110. That's 2's complement minus 2. If I were to create an 8-bit number out of it, I would have to extend the sign bit. See the sign bit in this column? To convert this to 8-bit 2's complement minus 2, you extend the sign bit all the way to the end, and you fill it with ones. 4-bit minus 3 in 2's complement is 1101. If I were to create an 8-bit minus 3 in 2's complement, I'd take the signed bit and extend it out to 8-bit. Signed numbers require extending the sign bit. That's called signed extension. This is unsigned binary multiplication. There are other algorithms that do exist for doing binary multiplication. The CPU/ALU designers also must decide how much is done with logic gates and how much is implemented in microcode. For computer science majors, it's more about understanding integer overflows and rounding errors on floating point calculations. You need to understand how binary multiplication works so you can understand when integers overflow. You cannot just multiply two large integers and expect the result to store in the same amount of bits. It's going to require more bits. Understanding binary multiplication is important for understanding integer overflows. Binary unsigned division. Computers are simple. All they do is move some ones and zeros from RAM to the CPU, manipulate or change those ones and zeros in the CPU, then move the ones and zeros from the CPU back to RAM. Then they repeat it a billion times a second. And that's where the real power of the computer comes from, the ability to do this a billion times a second. The ALU, arithmetic and logic unit, is now part of the CPU. In the old days, it was often a separate chip. But today, you generally integrate the ALU with the CPU. And it's the ALU that performs the unsigned binary division. Binary division of unsigned integers is remarkably similar to decimal division. Start with decimal division and look at where it's similar before doing binary division. Take the value 51318 and divide it by 226. I usually do not start division with leading zeros, but they will be important when we do binary division. It is important to understand why those zeros are here. 226 fits into 5 0 times. You take this value and you try to insert it into 5. It doesn't fit. You put a 0 above the 5. 226 fits into 51 0 times. Once again, 226 does not fit into 5 1, so you put a 0 above the 1. This should be 4th grade review. The value 226 does fit into 513 two times. 226 fits into 513. After subtracting 2 times 226, or 452, from 513, there'll be a 61 left over. Once again, this fits in twice. So above the 3, we write a 2, and then we calculate the remainder of 61. Drop the 1 down. Drop the 1 down to the 61 and make 611. 226 does fit into 611 twice, so we'll write a 2 above the 1. After subtracting 2 times 226, or the 452, from 661, there'll be a 159 left over. Let's drop the 8 down to make 1598. So see that 8 right there? It gets dropped down and added to the 159 to make 1598. 226 fits into 1598 7 times. Since 226 fits into this number 7 times, we write a 7 above the 8. 7 times 226 equals 1582. Let's subtract that from 1598, and you can see we have 16 left over. That is decimal division. You should remember that from the 4th grade. 51318 divided by 226 is 227. 227. The final answer is 00. The remainder of this division is 16. Here's the remainder down here. Here's the answer up there. Very important to line up the columns carefully when doing division, especially binary division, where everything's going to be a 0 and 1, and there are going to be a lot more digits. Binary 133 divided by binary 9. For reference, the decimal calculation is on the left. 9 fits into 13 one time, so I write a 1 above the 13. Subtract out the 9 and get a remainder of 4. Drop the 3 down to make 43, and 9 fits into 43 4 times. 43 minus 36 has a remainder of 7. Before we start, keep in mind that 9 fits into 13 one time, and 9 fits into 43 4 times, and that's how we generate our result. I start the binary division with leading zeros to make sure I create an 8-bit answer and make sure I get the correct column for the leading one. Understand why these 4 zeros are there. 1001 fits into 1 0 times. This value fits into that 0 times. 1001 fits into 10 0 times. I'm looking at just these 2 digits, and my operand here does not fit into those 2 digits, so I write a 0 above it. 1001 fits into 100 0 times. Again, I'm just looking at these 3 bits. 9 Binary 9 doesn't fit into those 3 bits, so I write a 0 above them. Finally, 1001 fits into 1000 0 times. Gone all this way, the first 4 digits, none of those can accept or fit this value, so I put 4 zeros above them. This is where it gets easy. In binary, 1001 can only fit 1 or 0 times. 1001 fits into 1000 0 times, so this is a 0. 1001 fits into 10000 1 time. Into this value right here that I have boxed out, this number can fit once. When it fits once, I write a 1 above that column. Since it fits 1 time, place a 1 directly over the last 0 in 10000. Lining up the columns is hugely important. Very hard to get the correct answer with crooked columns. Subtract binary 10000 minus 1001. If you can do that, great. This is what I do. I convert them to decimal. Write the powers of 2 above my 2 decimal numbers, and it turns out this subtraction is 16 minus 9 in decimal, which equals 7 or 111. Write down the result of the subtraction, 111 here. I think conversion to decimal is the easiest. With the result of 111, I'll drop the 1 down from the next column, this one right here. I'll drop it down to form binary 1111. My operand 1001 easily fits into this result. After I drop the 1, I'll place a 1 above it to indicate that we can fit into this value. 1001 easily fits into 4 ones, so place a 1 over the dropped 1. It fits. Once again, we need to subtract binary. We've got 4 ones minus 1001. If you can do that, great, but this is what I do. I convert it to decimal. I'll write the powers of 2 below the 4 ones, and I'll subtract out the second operand, and this is 15 minus 6, or 6. The answer to this subtraction is 110. I'll write down my 110 here. A conversion to decimal is the easiest. With the result of 110, drop the 0 above it down to form binary 1100. Guess what? 1001 easily fits into 110, so I'll place a 1 over the dropped 0 because it fits. If it fits, you must put a 1 above it. If it doesn't fit, you put a 0 above it. Subtract binary 1100 minus 1001. If you can do that in your head, great. But what I do is quickly convert it to decimal. 1100 minus 1001 is 12 minus 9 equals 3, or 11. I think a conversion to decimal is the easiest way to do it. Here's my result, 11. I'll drop the 1 down from this column to form binary 111. 1001 does not fit into 111, so I'll place a 0 over the dropped 1. When there is no fit, you put a 0 over the dropped bit. No more bits remain. The division is done. 1110, which is this top row here, if you put it over 8421, you can see it's 8 plus 4 plus 2. That's 14, and it matches my decimal arithmetic. When I did binary division, I got the same result as my decimal division. I'm feeling pretty good about my result. The binary result of 00001110 is correct because it matches my decimal division. No more bits remain. The division is done. Let's check the remainder. The remainder of my binary unsigned division is 1111. Putting that over the powers of 2, 4 plus 2 plus 1 is 7. The remainder also matches my decimal calculation. Binary remainder of 111 is also correct. Notice how I checked my results. Decimal division, result, and remainder matched the result of my binary unsigned division, result, and remainder. This is unsigned binary division. Other algorithms do exist for doing binary division. CPU/ALU designers also must decide how much of this is done with logic gates and how much of it is implemented in microcode. For computer science majors, it's more about understanding integer overflows and rounding errors on floating point calculations. Whenever you do division in binary, you're going to get rounding errors. You need to understand binary division to understand why and how much rounding errors occur.
GameSci.com.